states that for any cycle, a system or control mass undergoes the cyclic integral of the heat is proportional to the cyclic integral of the work. So then if the system goes round in a cycle, so starts from a certain point in thermodynamic coordinates. So the thermodynamic space is the space spanned by the thermodynamic coordinates. So this has the independent coordinates are the number of independent thermodynamic variables which you have to specify in order to specify the thermodynamic state of a system. So typically for a pure substance in one phase, it would be two variables, pressure and temperature could be possible choice. So if you specify pressure and temperature, everything else is specified. So then in that space, a thermodynamic state is specified by the number of independent variables that you have. So once you have specified pressure and temperature, the thermodynamic state is specified. So if it goes round in a cycle, then it starts from a certain point in thermodynamic space, and once it comes full round in a circle, in a cycle, it comes back to its original state. So if it comes back to its original state, then the first law of thermodynamics states that the Q supplied to the system must be proportional to the W done by the system. Or if W is the input, then Q must be the output. So a constant of proportionality was initially put there because at one time the units for Q and W were different. But once we switched to SI units, we started using joules and kilojoules for both W and Q. So then the factor J becomes unity, and if it's unity, it can be dropped. So it says that if the system goes in a cycle, that is, it comes back to the point from which it started, then over that cycle, the integral of Q and the integral of W must be the same. So from this, we'll try to deduce a certain quantity which will show is a thermodynamic function. So then let us consider a point 1 and a point 2. And let's say I go from point 1 to point 2 following a path A. And then from 2 to 1, I come back following two different paths, B and C. And let's say B and C could be any arbitrary paths. The only requirement is that it should start from state 2 and finally reach state 1. In that case, one possible cycle is the system goes through path A and returns through path B. The alternative cycle is it goes through path A and returns instead of path B through path C. So A and B together or A and C together, both of them constitute a cycle. So the first law of thermodynamics should be applicable to both possibilities. So A and B, if I consider, then it would be, so what I have is integral of delta Q is equal to integral of delta W if it goes through in a cycle. So for the first cycle, this would be 1 to 2 again for A and C, it would be sorry. Then if I subtract the first equation from the second equation, or okay, let me subtract the second from the first, then I would have now let me bring all the B's to one side and take all the C's to the other side. So then I have now when I drew this diagram, I said that B or C could be any arbitrary path as long as it starts from 2 and reaches 1. So therefore, for any two arbitrary paths B and C, this integral of delta Q minus integral of delta W seems to have the same value. So for B and C it is same, and B and C are any arbitrary paths. So therefore, whatever other path I take, I could use the same logic and show again that it gives you the same value. So therefore this so in a similar way, if we had constructed arbitrary paths from 1 to 2 and returned by the same path, again we could have we could have shown that integral of delta q minus integral of delta w from 1 to 2 is independent of path. So then the integral of delta q minus the integral of delta w from one thermodynamic state to another is independent of the path followed as long as the endpoints are the same. So then there must be some function of the point so that so then I could arbitrarily define a function of the point 1 to have a certain value, and then if I know the integral of delta q minus integral of delta w, then that difference I could take to be the difference in a thermodynamic property between 1 and 2. So what is the physical significance of that difference? So what I'm taking is between two arbitrary points, integral of delta q minus integral of delta w. So what does this represent physically? So if it is 1 to 2, so it is q added between state 1 and 2 and w So how much energy has been added as Q between these 2 points, and how much energy has been taken out as W between these 2 points? So that should give you the net increase in the energy of the system, because you have added this much, from that you are deducting how much you have taken out. So that difference must have remained with the system. So therefore, we define so this is the, so E is the energy of the system. Now, if I choose a certain point as 1, assign a certain value to E at point 1, then given any other point 2, I just have to measure delta Q and delta W for any path between 1 and 2. And the first law of thermodynamics tells, from that we have deduced that regardless of the path, this difference will have the same value. So we take it by any path, measure the integral of delta Q and the integral of delta W between point 1 and 2. So then we have the quantity on the left hand side. If we have taken an arbitrary value for E1, from this we can calculate what is E2. So this provides the definition which allows us to calculate energy at any point. Now comes the part which the macroscopic thermodynamics cannot really prove. So these are the situations where we have to keep in mind that the macroscopic description is actually an averaged description of a microscopic state which has finer details which we choose to ignore in the macroscopic model. So then the energy which we define here consists of, as we said, kinetic energy, potential energy, and internal energy. Now, what is this internal energy? This internal energy is what was called caloric. Now, today we know that there isn't a fluid called caloric which flows from higher temperature to lower temperature. This extra energy is actually energy of microscopic motion. So the it could be random motion of gas molecules which are moving in straight lines until they go and collide with another molecule. Now, if you consider molecules to be hard objects like a set of marbles, in that case, it follows a straight line from one point until it goes and actually hits another molecule. But then the molecules are not hard spheres. So therefore, there is a force of interaction between molecules which follows a certain law depending on the distance between the two molecules. So if we take that into account, the path of a molecule is not actually a straight line, because although it may not go and collide with another molecule, it still experiences a force exerted by the other molecule. Now, let's not go into all those finer details. This internal energy which we say is actually the energy of the molecules at the molecular level. So in a gas, it could be straight line motion. So the kinetic energy of that motion in straight lines. In a solid, it could be vibration of the molecules in a lattice. So all that is actually included in this internal energy. The microscopic, the molecular motion could be could have various forms. It could be lattice vibrations. It could be molecules moving through space. But whatever it is the kinetic energy of the microscopic motion of the molecules. Now comes the assumption which macroscopic thermodynamics doesn't really tell us. But once we understand that kinetic energy is the energy because of the bulk motion of the material. So this depends on the velocity of the center of mass. So that is when you talk of a lump of material and take its center of mass velocity, you are ignoring the microscopic motion. Similarly, when we talk of potential energy of a macroscopic object, we are taking the position of its center of mass and seeing and then using the existing force field. So we may take into account the gravitational field, and using that we calculate what is the potential energy. Now both of these ignore the microscopic motion, and then again the internal energy takes into account the microscopic motion only. So then from this what emerges is that there are two sets of variables. One is the macroscopic position and the macroscopic velocity of the object. So if you have a lump of iron, you can measure its position, you can measure its velocity, and that gives you what is the potential energy, what is the kinetic energy. But then how much total energy does it have would also depend on how hot that block of iron is. So that is contained in the internal energy. So then from this understanding, what we say is that while the kinetic energy and the potential energy depend on the physical coordinates, so if I take my coordinates to be, so if I there are two manners of speaking. In one manner, you say that coordinate means the position only. In that case, the macroscopic state is specified by the coordinate and the velocity. So the coordinate and the velocity determine the potential energy and the kinetic energy. And then the internal energy is determined by the microscopic motion. So then what from this what we can guess is that while the kinetic energy and potential energy depend on the physical coordinates, the position and the velocity, the internal energy is independent of the physical coordinates. So an object a block of iron which is at say 100 degrees centigrade, what we can guess from this is that if a block of iron is at 100 degrees centigrade, the energy of internal motion of the iron molecules in that block will not depend on where that block is, or on the velocity with which the block is moving. So then what we are saying is that the kinetic and the potential energy, which depend on the gross position and motion of the body, depend only on the physical coordinates of the bulk position. The internal energy does not depend on those external coordinates, on those physical coordinates. It depends only on the thermodynamic state. So there are two sets of energy. One is the energy of the bulk position due to the which depends on the bulk position and the bulk velocity, and that depends on the location of the object and its bulk velocity. On the other hand, the internal energy, being internal, does not depend on where it is the object is located. It does not depend on the velocity with which the object is moving. It depends only on what the thermodynamic state is. So if the thermodynamic state is specified, that specifies the internal energy. Now that is something which we cannot prove from the first law, but from our understanding that what is kinetic energy, what is potential energy, what is internal energy, uh, from that we come to the conclusion that internal energy depends only on the thermodynamic state of the system. So then we say that so if you specify the number of independent thermodynamic variables, then your internal energy gets determined. So therefore, internal energy is a function of the independent thermodynamic coordinates. So that is what is called a thermodynamic function. So we write, so in fact, if this path from 1 to 2 is taken as a small elemental path, then we could write so this dE so this U, so this is a convention followed in thermodynamics that the an extensive property is usually denoted by a capital letter, and the corresponding intensive property is denoted by the corresponding small letter. So maybe I should have written this as M. Okay, so then I'll just introduce one more definition, which probably you have already studied in school, but then let's just go through that, recapitulate that once again. We have introduced a quantity called the internal energy. So we said, okay, the first law of thermodynamics defines a quantity called the energy of the system. Now that by physical reasoning we said should consist of the kinetic energy, the potential energy, and something called internal energy. And this internal energy is a function only of the thermodynamic coordinates. So then the first law introduced energy. We divided that into the macroscopic energy and the microscopic energy, and the microscopic energy is called internal energy. Now there's one more term, the enthalpy. So what exactly is that? So let's consider a simple situation. We have a piston, we have a cylinder with a piston, a certain weight is provided on it, and we have a fluid here. We assume that the only work done by the fluid is on the piston. So the fluid is exerting a certain force on the piston. So then, if we assume that the only work done by the fluid is on the piston, that will be the force. The force is the pressure into the area into the displacement integrated over displacement. So this is the area and this would be dz. Now if the piston is moved by a distance dz, the volume of the fluid changes by area into dz. So then I can write this as pdv. By the first law of thermodynamics, So we had delta Q minus delta W equal to du. So I brought the delta W to the right hand side. Now we know that in this case, the delta W is P dV. We have assumed that changes in kinetic and potential energy can be neglected. If the fluid is there in the cylinder, it's at rest between one thermodynamic when it is in equilibrium. So kinetic energy can be taken to be zero. There's some, as the piston moves up, there's a slight change in potential energy. We assume that that can be ignored. So then, instead of dE, we have written only du.
So, but when we will integrate, it will increase, like it will be some finite quantity for potential energy.
Yes, it is a finite quantity. It will not be non-zero. But if you calculate the magnitude, usually the thermal energy is of much larger magnitude than the potential energy. So I'm just giving you a hand-waving argument. What I would suggest, for a certain, assuming a certain amount of gas, why don't you do the calculation? It should turn out that the change in potential energy is small compared to the change in thermal energy. So why don't you do that exercise and see what it gives you? In case it doesn't, then we'll discuss it. Okay. Constant volume heat addition means so I clamp the piston in place and put a burner under the cylinder and heat it. And I just want to see how much Q I need to add in order to change the temperature by a certain amount. Then the delta Q I require would be equal to du. So then so the capital CV denotes for the entire gas, and small cv would be so I've divided the capital U by the M. That gives me small u. So the specific heat is the partial derivative of the specific internal energy with respect to temperature at constant volume. Now, since the pressure is constant, I can write this as so then we define so this is the definition of enthalpy. So for a constant pressure process, so for a constant pressure process, we found that delta Q is dH. So we had capital H is equal to capital U plus PV. So if I divide by M, I get okay. Now after this, having defined what is internal energy, what is enthalpy, our next task would be to apply the first law of thermodynamics to an open system. So to a control volume where you have material flowing in and flowing out of the control volume. So once I start that, that will take quite a bit of time. So I think this would be the right time for taking a 5-minute break. So during the 5-minute break, let me just discuss how to plan for the weeks ahead. So if I look at the academic calendar, I realize that I hadn't really read it very carefully. So the timetable slots, it says that 6th to 10th of September, suggested windows for tests as per regular class timetable schedule. Other classes will continue as per timetable. So tentatively what we can plan is 10th, 6th to 10th, if I see, six to 10, during this week, we have a double lecture on 10th. So during this time, so on 10th, we can have our class test. So the logical thing to do would be to complete thermodynamics and then have the class test. Now, by then, whether we'll be able to finish thermodynamics, at the moment, I'm not quite certain. Maybe we would be, maybe we would not. So, but then, since we need to have 3 class tests, it's probably best not to delay things and to respect whatever has been suggested and have a class test on 10th. So depending on how much we have covered, that will determine the course. So we can have a class test on 10th. Now what it does not tell us, what should be the duration of the class test? Because last year the instruction was the class test should be of duration approximately not less than 1 hour. So if that be the guideline, our class test could now we have a 2-hour slot. So depending on what we want, it could be anything between 1 to almost 2 hours. So probably at that time we'll discuss how long that test would be. So tentatively, maybe on 10th of September, we'll have a class test.
So can you give like some idea like what kind of test will there be like MCQs or numericals? What kind of questions?
Actually, I was waiting for instructions from the authorities. Now, it seems the authorities have just left it to us. Now, MCQ is something the students would very much like. But my personal feeling is the MCQ doesn't always provide a good measure of your understanding. So if we don't have an MCQ test, how do we hold it? So in the past, what I did, I used to have a test similar to what you normally have when the test is held in offline mode. So what I would do, I would send you the question paper, a question paper which looks like the conventional question paper with long problems, and then the instruction was that you be ready with paper and pen to write a conventional answer. So you would write it with pen and paper sitting in your house. So there would be a deadline on it. Now the instruction was I would identify a set of final answers which had to be emailed. So that has to, so if it's a 1 hour exam, the final answers have to be emailed within that deadline of 1 hour. After that, you would get 10 more minutes to scan your detailed answer script, which is the conventional sort of answer script. Scan that and email it to me, and that has to be done within 10 minutes. And the additional thing which I used to do, and which I'm a little interested in trying it out, because last time I had a very small class. This time we have a moderately large class. We have 81 registered students. So then what I used to do, I used to have what I would do, I would change the, so if it's a long problem, a few of the input quantities I would change for different students. So then at that time I used to put it in manually, but for a larger class, I didn't do it because the class was small. Now that we have a larger class, I can have a software for generating that. So what it would do, if I have a number of inputs, A, B, C, D, E, F, in a problem, typically you have a number of input quantities. Like last time we had those diameter, temperature, pressure, etc. If you remember. So we had 4 on one side, 3 on the other. So you had 7 quantities. So then what I would do, I would choose, say, 3 of these, and then those 3, I would have a program which either uses say an arithmetic progression or a geometric progression, or I could have use a random number generator. So it would take a base value and put a random deviation on it. So then it would generate a set of values for some 3 of those parameters. So out of that A, B, C, D, E, F, etc. Let's say for B, D, and F, I choose a set of values. After that, what I have is, I have a program which generates. So, and then you would be told what are the that instruction will be given. So then I would tell you what are the final answers which have to be emailed back to me. So then I would have a program which, given those input values of those parameters which I change, if I give those 3 parameters, if I give the values for that, it will generate the final answer. So in that case, if I have a set of input files, one input file would contain your roll number and name. Another input file would contain the values serially for all the students for that few parameters which I have changed. So using these two input files, it should generate an output file which will be the set of answers for the different students. So then the whole idea of doing this exercise is that the final answers would be different for all the students. So that rules out the possibility of students copying the final answer from one another. Lead us not unto temptation. So then in that case, because invigilation becomes very difficult when you write the exam from home. So if this thing again works out, which I hope it will, then you, so this is the mode in which I used to conduct the exams. So I still believe, instead of giving you MCQ questions, this would provide a better assessment of your performance, because in the past, the MCQ and online exams, some subjects were done in that manner, and that was before the pandemic, and there was complaints from, especially from the students, that is not giving a proper assessment. So keeping that criticism in mind, I believe instead of a MCQ a type of exam, I would try to simulate a normal exam sort of environment for the test. Okay. So, okay. Huh.
So for the portion for the exam on 10th will be the portions taught till 9th.
Yes, it could be the portions taught till 9th, which seems a little unfair, right?
Yes, sir.
Okay, so then what I'll keep in mind that probably the portions taught till 3rd would be more reasonable.
Okay, sir.
In that case, the portion for 8th and 9th will have to be covered in the next test. So depending on how we progress, we'll think of that. I also understand that whatever covered till 9th, you don't get the time to work out relevant problems. And for a subject like this, some amount of time when you can work out the problems needs to be given. So it seems, so if I include the material on 10th, I can only give MCQ questions based on material covered on 9th, which I don't want to do. In that case, I think reasonably whatever we cover till 3rd can be the syllabus for the test on 10th. So depending on how we progress, we'll decide. So I think at this point we'll discuss once again before the exams, what should be the syllabus. Okay, it shows 67, of which 2 is me. Is it? No, I think only. I think unlike the Google Meet, I am seen as only one individual. In that case, I hope there are 66 out of 81. Okay, so that attendance it has downloaded. So henceforth we'll be taking attendance. This is the first law. This is the conservation of energy. Whatever Q added to the system minus the W taken out would give me the change in energy. So to a system, this law of conservation of energy ought to apply. Writing it in terms of rates. So the control volume could be a turbine where there is material coming in through the inlet pipe, leaving through the exit, and work being done. There's a work output from a shaft. So then this could be my control volume. Or I could have a heat exchanger I have two pipes. Say I could have a hot fluid flowing through one, and there's another cold fluid flowing through the other. So the hot fluid transfers Q to the cold fluid inside this heat exchanger. So this could be my control volume, and this is the control surface. This is the control volume, this is the control surface. So if my physical quantity is the energy, so E, in that case, in place of capital B, I put E, and in place of beta, I put small e. So this is what the Reynolds transport theorem tells us. So that is what I need to put in over here. Now, that would seem to tell me what is first law applicable to an open system. Now, there's a little bit more that we need to do. That this W dot system actually has two parts to it. So if I look at this particular example, then that difference will come out, that what is the so this W dot system is the work done by the system. So the system consists of the working fluid which is flowing in through the inlet pipe and flowing out through the exit pipe. So the W dot system is the total work done by this working fluid. Now that, if you think carefully, you'll realize that there are two parts to it. My system, by definition, consists of a certain mass of material. It encloses a certain mass of material. So that material, so my system boundary at any instant of time may be somewhere here. So if I consider at time t, my system boundary is over here. Now, the W dot sys is the total work done by that amount of material in the system. Now, that does work in many ways. One way is the work which it does on the shaft, which is extracted as energy from the shaft, which is used for driving the generator. So this is a turbine connected to a generator. So some amount of work so the fluid pushes against the vanes of the turbine. So as a consequence, it does work on the turbine blades. That work is transferred through the shaft to the generator. Apart from that, the material in the system also does work at the boundaries of the system. So in the exit pipe, so here at the walls of the turbine, there is no motion. So there is a force exerted by the gas, but there is no motion, so no work is done. But at the boundary of the system, the system boundary is moving with the velocity of the material. So therefore, not only, so at any instant, the boundary could be somewhere here, and then not only is the material in the system exerting a force on the material outside, that point of application of the force is also moving with time. So it is doing certain amount of work. So then the material in the system pushes the material, pushes on the material across the boundary of the system. And therefore, since it's exerting a force on the material outside, it is doing certain work on the material outside. So if I talk of the system is actually doing work on material outside. So that amount of energy is actually expended by the system. So that has to be taken into account while considering the total work done by the system. So there is a certain amount of work which it does on the shaft and a certain amount of work which it does at the boundaries of the system at the point of flow into and out of the system. So then the W dot system consists of W dot CV plus W dot flow. Now at the exit, what is the work done by the system? The system is exerting a pressure P and the motion is in the direction of the force. So then the work done by the system is positive over here. So that is PE into AE so ZE is the displacement normal to the exit. So the force exerted is PE into AE into the displacement that gives you the work. And at the inlet, it is the material outside which is exerting a pressure on the material inside, and the displacement is in that direction. So the material outside is doing work on the system. So that by convention is negative W. Now AE into DZE is the volume through which the extra volume covered in time delta t. So this I can write as PE okay, maybe I didn't really require this step. I can directly write AE DZE is VE into delta T. So I've written VE rho E because VE is the reciprocal of rho E. So V into rho E has to be unity. VI rho I has to be unity. So this factor I have added, which is actually unity. Rest is same as what I had here. So this is the flow work. This is the flow work in time delta t. So in as a rate, if I write, it will be Now just recapitulating, in time delta t, the fluid flows out by covering a distance v delta t. So then the extra volume covered in time delta t would be AV delta t. So in time t, so if I have a cross-sectional area A, in time delta t, it would cover an additional space of uh, extent V delta t. So the extra volume dV would be AV delta t, and the extra mass would be rho AV delta t. So dm by dt, the mass which flows out, would be rho AV. So therefore this is so then I find when we had the wrote the Reynolds transport theorem, we had, because of a flow at the inlet and exit across the boundary of the control volume, because of that flow across the boundary, we had terms involving ME dot and MI dot. Now similarly, when we calculate work done because of pressure across the boundaries where inflow or outflow is occurring, we find similar terms occurring. So then we can put all this back over there. Okay. So we know this for a system. Now the DE system by DET we have written in terms of control volume using the Reynolds transport theorem. The W dot system is W dot sys is W dot CV plus W dot flow. So the W dot CV is what is the work done by the fluid inside this volume. So inside this volume, it exerts a force on the impeller blades, and that it does some work. So that is the work in the control volume. Sometimes it is denoted as W dot shaft, and you have a W dot flow, which doesn't actually come out as useful work. So that is why we make this distinction, that this W dot CV is the useful work which we get from the system, and this is what is naturally done at the inlet and exit. So then W dot system is this. W dot flow, we have an expression. So I can write sorry. And the Q dot system, so whatever Q, so W, why did we make this distinction? Because the work done at the boundaries doesn't, so that doesn't come out as useful work. So that's why we ignore that. Now the Q dot to the system, whatever Q supplied is what you have to pay for. So then there doesn't seem to be any distinction between Q dot system for the Q dot for the system and Q dot for the control volume. So I write this as Q dot control volume. So then I had So I had written this assuming there's only one inlet and one exit. If there are multiple, then I have to put a summation sign over this. Now if I write the full expression for E, so I'm writing small e, so then I have to take the kinetic energy and the potential energy per unit mass. So per unit mass, this is what it would be. So that takes care of these two terms. Now if I combine this with this, I have so then this I have written down, this I have combined with this I have combined with this, then I am left with now if I look at these expressions, I find that I have this combination U plus PV. Now that we know is equal to H. So the first law for an open system looks similar to the first law for a closed system, only that instead of having dE system by dt, you instead have a del of E of the system, del of E of in the control volume with respect by del T plus the flow terms, the whatever is flowing out minus whatever is flowing in. Now there you'll observe a difference that while the partial derivative of the energy in the control volume is contains the energy alone, the so the Reynolds transport theorem tells you that the change for the system is not just the change in the control volume, but also has contributions from whatever is flowing in, whatever is flowing out. So then the change in the control volume has U, but the rate at which the property is flowing in and flowing out, that has H. So this H comes because of the flow work done at the boundaries. Now, if I have an open system where no Q is supplied and no W is done, and it is operating at steady state, then this outflow must be equal to this inflow. So the enthalpy plus kinetic energy plus potential energy flowing out must be equal to the rate at which it is flowing in. Now, if I assume that when we do the problem, we'll see that quite often it's true that the internal energy or enthalpy is much larger in magnitude than the kinetic energy or the potential energy. If that be so, then I could neglect the kinetic energy and the potential energy. And in that case, if I have steady state, steady flow, no Q dot, no W dot, what this would tell me is the enthalpy flowing out must be equal to the enthalpy flowing in. Then again, a point which people often tend to overlook. What happens if the enthalpy flowing out and the enthalpy flowing in do not match? In that case, it does not result. So then that gives you the rate at which changes occur inside the control volume, because the outflow and inflow are not the same. So if there is a mismatch in the enthalpy flow, that gives rise to a change in the internal energy. So in this term, it is internal energy, and in this term, it is enthalpy. But most often we'll be dealing with steady state, steady flow, in which case this term becomes identically zero. So that is why we often overlook this point. So for an open system, and if we have steady state, steady flow, in that case, this is the statement of the first law. So whatever the enthalpy plus kinetic energy plus potential energy flowing out minus whatever is flowing in must be equal to Q dot CV minus W dot CV. So it becomes enthalpy and not internal energy, because we have taken into account the flow work and included that in the flow terms rather than in the rate of work done term. Because the flow work is not really what we get as useful output for a turbine, or what we have to put in as expenditure in a pump. So then if we separate the rate of work done into a part which is shaft work and a part which is flow work, then the flow work gets included in the flow terms, and because of that, instead of U, we have an H in the flow terms. Now that we have defined two more quantities, the internal energy and the enthalpy, let us go back. Now once again, quite often we'll be dealing with systems like what we were dealing last time. If you have a steam turbine, you have steam coming in, steam going out, comes in at a certain thermodynamic state, leaves at a certain other thermodynamic state. So therefore there's change in properties. And because of that, if it's a compressor, you might have to do work on it. Or if it's a turbine, you could get work output from it. And that is what we need to calculate. So then again that question comes, if I am dealing with a steam turbine and I know the thermodynamic state, the temperature, the pressure and temperature at the inlet and the pressure and temperature at the exit, how do I determine the properties? So let's go back Okay, so this is that same table which I showed you last time and which I've emailed to you. So then in the beginning it has the saturation part where you have a mixture of vapor and liquid. So to how much liquid, how much vapor, those questions would arise. So let's go to a simpler part. Let's go to the compressed water and superheated steam part. So waters are cooled and steam superheated. So if we go back to our earlier problem, we had steam at 20 megapascal and 600 degrees centigrade. So this is 20 megapascal and it's at 600 degrees centigrade, which we had seen as superheated steam. So for each, for this value of pressure, it's tabulated, properties are tabulated for various temperature. So for any temperature, last time we wanted only the specific volume. So we saw only, so we read off that value from the second column. Now let's see the further columns. The next column is U and the column after that is age. So if I go to 600 degrees centigrade, then the U and the V are 3175.3 and 3539.0, and the units are, this is energy per unit mass. Internal energy is energy per unit mass. So that has to be in kilojoule per kg. So if we require the values, we want to apply first law, then for steam, this is where we can get the values from. Now, so if it were, say if it were, so if you are dealing with a power plant, in a power plant, typically you have a pump which raises the pressure of water, raises it from atmospheric pressure to a higher pressure. Then at that higher pressure, it is sent to a boiler. Q is added to it by burning fuel. So then it reaches a higher temperature. And then that steam at higher temperature and higher pressure is sent to a turbine where it undergoes expansion. So now, if I'm looking at the turbine, if I don't want condensation in the turbine, the values from this for superheated steam would be good enough. That is what we had in the example which we saw last time. If I consider the pump raises the pressure when it is still water, because the pump is before the turbine. You place it before the turbine, which is before the boiler. You place it before the boiler because then the pump will have to handle less volume of material. So if it's in the liquid state. So then if I want to apply first law to the pump, then I look at the values before this line. So this line marks the boundary between liquid and vapor. So if I'm dealing with subcooled liquid, I can similarly get the values of U and H from here, and that H I can use if I want to apply first law of thermodynamics for an open system to a pump. So for subcooled water and for superheated steam, these are where we can get the values of U and H. Now, coming to the temperature-based saturation properties, saturated water and steam temperature-based, given a certain temperature, so depending on the pressure, it will boil at a certain temperature. So let's say the pressure has been determined in such a way that water boils at this temperature. So then we are given two values for both internal energy and specific internal energy and specific enthalpy. One value is given for the liquid and the other is given for the vapor. So UF is for the liquid and UG is for the vapor. Similarly, HF is for the liquid and HG is for the vapor. In fact, there's one more property given, HFG, which is by how much HG exceeds HF. So if I subtract HF from HG, so from this 2600 something, I deduct 300 something, it will give me 2300. So HFG is the difference of these. Now the question comes that inside the boiler, if I want to do an analysis, at some point I may have a mixture of liquid and vapor flowing. So in that case, for a mixture, so in the saturation region, so if I'm in the superheated region, I have only vapor. If I'm in the subcooled region, I have only liquid. What if I am in a situation where the phase change is occurring? In that case, I have a mixture of liquid and vapor. So given a mixture of liquid and vapor, how do I determine the enthalpy? So if I want to apply first law to a system, so if I want to say apply first law to a control volume, where at the inlet and exit, what is flowing across is not pure liquid or not pure vapor, but a mixture of liquid and vapor. If I want to apply first law of thermodynamics to that control volume, how do I determine what is the enthalpy at the inlet or the exit? So we had defined the quality which is denoted by X this is the fraction of mass which is in the vapor state. So then if I what is now let me reason out what is the specific internal energy of a mixture of vapor and liquid and vapor. So the specific internal energy would be the mass of liquid and the contribution of the liquid to the internal energy would be the mass of liquid into the specific internal energy for the liquid. Similarly, for the vapor, its contribution to internal energy would be this, and this would be the total internal energy divided by the total mass, which would be this. Now this we know by definition is X. Now if I add this and this, it would give me MF plus Mg by MF plus Mg, which is unity. So this plus this is unity, this is X, so this must be 1 minus X. So if you know the quality of steam, and UF and UG we found are given in the table. So given whatever the quality, you can calculate what is the specific enthalpy of steam of that quality. Now these tables were actually made at a time when electronic calculators had not been invented. So therefore, doing all these small arithmetic calculations took time. So people always tried to minimize the effort which would be required. So then people said, okay, I'll have to calculate 1 minus x multiply by this, multiply x by this. So quite a few arithmetic operations are required. Let me regroup it. This I can write as UF minus XUF. So as you increase x, if x is 0, it will that means it is entirely liquid. The specific internal energy would be the value at the liquid. As you increase x, it will increase in proportion to x with a rate by how much the U for the vapor is larger than that for the liquid. So this is the internal energy of vaporization. So then this was defined if G is determined by so then this would be so then calculating 1 minus x and multiplying that by UF, that part you no longer have to do. So you take the value of for the liquid and multiply by x the value for vaporization, add that to it, and that gives you U. Similarly, your H is so that more or less covers the theoretical explanation of the first law of thermodynamics. So in the next class, we'll do one or two problems so that whatever expression we have derived, you get to see how it is actually used for predicting the behavior of typical engineering systems. So the examples we'll do in the next class. Once we finish that, then we'll go over to the discussion of second law of thermodynamics. So I'm going at a steady pace because the syllabus as it's given seems to cover the syllabus of two courses, thermodynamics as well as basic fluid mechanics, all in one semester, and that too squeezed by a month relative to what it normally should be, which is obviously not feasible. So then since you are also studying other subjects and since I'm also trying to do some other work, let's not try to overstrain ourselves. Let's go at a pace following the regular timetable and see how much we can cover. So what to include, what not to include, as we progress, we'll have to take that decision. So next class I'll do a few examples for the first law and then we'll go over to second law. And I'm emphasizing more on the fundamentals because unless we understand the fundamentals, applying it to engineering systems without knowing the fundamentals would not be advisable. So when I have to cut down, I'll try as far as possible not to cut down on the fundamentals. Okay, if you have any questions, you can ask. Okay. Yes. Okay, then we'll close
Sir?
here. Yes.
Sir, you tell that the enthalpy of steady flow is different from the control volume enthalpy, right?
Enthalpy of?
That's the at exits means what I-
No, enthalpy is the same whether you're considering a closed system or an open system. Enthalpy by definition is U plus PV. It just so happens that when you apply first law to a system, then what you have to, then the difference of the energy supplied minus the energy taken out gives you the change of internal energy. But when you have a flow system, that when you consider the flow terms, you have to consider the enthalpy outflow and the enthalpy inflow rather than the internal energy inflow and internal energy outflow.
Okay.
So for the flow terms, you have to take into account the enthalpy. This difference comes about because we have to include the flow work. So when we include the flow work, we find that the flow terms, instead of the difference between the net outflow and the net inflow, that has to be in terms of enthalpy rather than internal energy, so that the flow work is also taken into account.
Okay, got it.